In this video, we are going to do an example of a direct proof. What we're going to prove is a somewhat well-known fact that we sort of take for granted, but what we're going to do is we're going to practice the rigorous outline that will be expected of you when doing a direct proof later on in the course, when things are less obvious or intuitive. So before we get started, what I want to do is outline what I think especially at a beginner level, should be involved in every direct proof that you do. So a basic direct proof should follow the outlined format that I'm going to put here. The very first thing you should do is state your assumptions. So sometimes your assumptions are given to you in the statement of what you're trying to prove. Sometimes you may be pulling in other assumptions and you need to make your reader aware of this, but that's the very first thing you're going to do. You're going to establish the ground from which you will be working. These are the things I will be taking for granted. The next thing that you should do is tell your reader where you're going. So when you state your assumptions, you're telling your reader where you're starting. I always have a to show statement somewhere in the proof that begins something along the lines of we will show that blah, to tell the reader where we're ending. So tell your reader where we start, tell your reader where we stop. And after that, what we're going to do is introduce necessary definitions, theorems, variables, things of that nature. So if one of your assumptions or part of your to show statement involves showing that a number is even, for example, then you should remind your reader what it means for a number to be even, or let them know which particular definition of even you will be using to make sure that you're on the same page. Similarly, if you have to introduce any variables in your proof, if you're going to let x represent some particular quantity, then you should state this here. From there, we begin the real heart of the proof. We start working and drawing conclusions from our assumptions, doing mathematics that we can always justify. So we'll do some sort of computation and we'll justify it. We'll make some sort of leap and we'll justify it as we go, stating what fact it is, what assumption it is, what the reader should be familiar with to draw that conclusion from what we have. And last but not least, we'll establish what we're trying to show. So we'll be doing our work going along, and we'll have started with one of our assumptions, which is what we told the reader we're going to start with, and we will end with the conclusion, which we've said is our end because we've had this to show statement. Now, let's get to it then. Here is the lemma that we're going to be proving in this video. So as a side note, a lemma is a statement of mathematical fact whose proof, and you use the word lemma instead of theorem or fact because you want to indicate somehow that the result is either small, not monumentally important, or that it's just going to be used as sort of a building block or a minor tool to prove something that's bigger, like a theorem. So lemma is a mathematical fact, but since we already feel really comfortable with the statement of this lemma, we'll call it a lemma because it's not groundbreaking. It's not going to change the world to know that if n is an odd integer, then its square is also odd. That's what we'll be proving today. Now, before we even begin trying to prove something, it's always a good idea to make sure that we are 100% certain of all words and terms that are defined in the statement of that fact. So here the relevant definition is that of an odd integer. So I'd like to just remind you the definition of odd that we will be working with before we start trying to write a proof. If we don't know what the lemma is saying, there's absolutely no way we're going to be able to prove it. And our definition of an odd integer, right? An integer n is odd if and only if n can be written as 2k plus 1, where the k quantity that we have represents an integer. That aside, let's begin the proof of our lemma. So following the format that we described before, the first thing we need to do is state our assumptions. In this problem, or I guess in this proof, the only assumption we need is the assumption given to us in the statement of the lemma, which is to suppose that n is an odd integer. That will be the thing that we're assuming. If n is an odd integer, then we're going to show that its square is also odd. So our assumption is suppose n is an odd integer. What are we trying to show? This was also given to us in the statement of the lemma. Our to show statement is, we will show that n squared is odd. And here I'm going to kind of blend into the next step, which is introducing relevant definitions. I'm going to elaborate further on what we're trying to show. I'll say we will show that n squared is odd. What will we do in particular? We will find an integer k for which we can write n squared as 2 times that k plus 1. And that's how we will show that n squared is odd. We'll write it in the form that we need according to the definition of an odd number. Now, necessary definitions is that things are odd. We're going to show that n squared is odd. We're going to show that n squared is 2k plus 1 for some integer k. But let's go back now and let's elaborate on our assumption. We are assuming that n is odd. What does that mean when applied to n? It means that n can be written as 2 times some integer plus 1. Now, note that here, under necessary definitions, I said n is assumed to be odd. That's our assumption. I wrote there exists L in the integers, such that n is 2 times L plus 1. Sometimes this confuses people. In the definition of an odd integer, I use the variable k to represent my integer. The reason that I chose to use L here at this stage in the game is that if I were writing a full and formal proof, I've already used the integer k up here. I've said we're going to find an integer k for which we can write n squared as 2 times k plus 1. So I personally want to set aside the letter k to denote whatever integer it is I need to write n squared as 2 times that integer plus 1. When I write L as 2 times an integer plus 1, chances are it's going to be a different integer, not the same integer that I need to write n squared as 2 times an integer plus 1. For example, if my n were to be 3, 3 can be written as 2 times 1 plus 1, but 3 squared, which is 9, can be written as 2 times 4 plus 1. So in this particular example, if n is 3, the k I would need to write n squared, 9, as 2k plus 1 would be 4, while the L that I need to write 3 as 2l plus 1 would be 1. So because k is standing for something specific, it's the integer that I need to write n squared as 2k plus 1, and L is representing the integer I need to write n as 2 times an integer plus 1, and these values could be different, I need to use a different letter to denote them. That's kind of a big long way of saying that I used L here because k is already taken, and this is part of the reason we use variables at all, because the alphabet has plenty of them, so that I have enough to get through proof. But anyway, that's a little technicality, but sometimes people get really hung up on why I'm changing my letters in between here and here, but I do think that that's a necessary step. Now, having established assumptions, our to show statement, and our necessary definitions, this is when the real work of the proof begins. This is where I need to start with what my assumptions are. Here I only have one assumption, and I need to work toward my to show statements, always justifying my work with solid mathematics. So I only have one assumption. There's really only one place I can start. I can start with using that n is odd. N is equal to 2l plus 1. Now I know where I'm going. I want to get to n squared. I want to, from n, somehow take a look at n squared. So it seems to me the best way to look at n squared is to take n and multiply it by itself. So let's do that. My first step is to substitute in the quantity 2l plus 1 for n, and then square. So n squared should be equal to, by substitution, 2l plus 1 squared. So my first step is to square n and to substitute in 2l plus 1 for n. And my next step then is when I have something squared, remember the 5th of November. No, remember, so important, that when I have 2l plus 1 and I'm squaring it, that I absolutely do not square that by distributing the square to each term. It's like a mathematical, unforgivable sin. And your math teacher's heart dies slowly inside whenever we see that error. No, when I take something like this and I square it, I need to expand it or FOIL it or whatever the word is that you're comfortable with. So 2l plus 1 times 2l plus 1, I need to combine all these terms, the 2l's times the 2l, 2l times 1, 1 times 2l, and 1 times 1. And after I do that expansion and I group like terms, what I'm left with is 4l squared plus 4l plus 1. So these two steps are often okay with people. First I need to substitute, then I need to expand, but then I'm going to do something that seems minorly arbitrary sometimes. Remember, what I'm trying to do is write n squared as 2 times something plus 1. As of right now, I've taken n squared and I've written it as 4l squared plus 4l plus 1. What I want to do next is I want to factor out a 2 from these first two terms so that I will be writing n squared in the form that I wanted to. So if I factor out just a 2 from these terms right here, I will have n squared written as 2 times something plus 1. So note that I could have factored out a 4l from each term if I was factoring out sort of the greatest common divisor that I know for certain, but that wouldn't be particularly helpful to me. Writing n squared as 4l times the quantity l plus 1, although I can do that, it's not particularly helpful for what I want to do, for where I want to get, because it doesn't stress that n squared can be written as 2 times something plus 1 per se. So here, I think this is perhaps the hardest part for people to swallow, is that what I want to do is go from n squared being written as 4l squared plus 4l plus 1 to trying to write it in the form that I needed from my to show statement. 2 times this quantity here plus 1. Now, continuing on, what I want to stress is, one of my assumptions was that L is an integer. Now, what I want to stress is that 2L squared plus 2L, which if you'll see is the thing in parentheses right here, 2L squared plus 2L, I want to stress that this thing, right, I've written as n squared as 2 times something plus 1. I want to stress that the something that I have right here is actually an integer, because that's my definition of an odd number. It can be written as 2 times an integer k plus one thing left. So that's what I'm going to do next. I'm going to stress that the thing that I have right here is an integer. Well, my justification for why that holds is that L is an integer. If I started with an integer, if I multiply it by 2, I'm still going to have an integer. So this 2L right here is an integer. And similarly, if I take 2L and then I multiply, which is an integer, and I multiply it by another integer, L, I'm still going to get an integer. Integers are what we call closed under addition and multiplication. And of course, then I take an integer and I add it to another integer, I'm still getting an integer. So because L is an integer, when I consider this thing 2L squared plus 2L, I'm also getting an integer, which is important for my definition. And at that stage, I've done exactly what I said. I found an integer. I said I was going to write n squared as 2k plus 1, where k was an integer. If I take k to be 2l squared plus 2l, then I've done just that. According to my work on the previous page, I've written n squared as 2k plus 1. We've shown that n squared is 2k plus 1 for k equal to 2l squared plus 2l. And that justifies what we wanted to show. And at that point, we said we were going to start with one thing. We said we were going to end here. We've shown that we're there. We're done.